I've had a long association with the APS. I took part in some of the early planning for beamlines back when I was a postdoc in the 1980s, and it's wonderful to see this continuing association and to see some of the new opportunities now with APS, looking forward to its upgrade. The talk I prepared here is one in which I thought I would give you an overview of some of the problems in the field of materials in extreme environments, and in particular pressure. This is a talk that will focus on sort of the phenomenology, some of the driving forces, some of the history behind this field, as opposed to some of the techniques and specific data that's emerged. And I'll use just a few examples, and in a sense are kind of archetypal examples that illustrate, in my view, how the field is developed and some of the exciting potential for the future, including what is possible in the future with the upgrade here. So, as you know, extreme environments pervade the cosmos, and there are quite a few. Energetic photon and particle fluxes, chemical extremes, electromagnetic extremes, and pressures and temperatures or thermomechanical extremes. And as I pointed out, today I want to focus on pressures and temperatures. That's really the area of my particular interest. But we also appreciate that we are interested in materials in multiple extreme environments. And I'll show a few examples of exciting new opportunities for studying materials in multiple extreme environments. So pressure is a particularly important one because it spans many orders of magnitude in the visible universe, from the kinds of pressures one has in intergalactic space to those inside a neutron star, clearly the domain of nuclear processes. The range of interest to us is really the range of conditions in nature found in planets, from the very large planets to our own planet here. And this is the range of conditions over which materials undergo chemical, as opposed to nuclear or plasma physics type transformation. So with myself as a chemist, this is an interesting area for exploring chemistry and new phenomena in a chemical sense with a broad range of applications. Here's a table to convert among the different units that I'll be using. So if you think about the effect of pressure on materials, we go back to the early days of physical chemistry and Boyle's equation of state, the effect of pressure on gases. And of course, an important correction to that it was that of J.D. van der Waals, who pointed out that a simple correction is needed to take into account the size of the atoms or the molecules in your system, and also a correction that takes into account the interactions between those atoms and molecules. And that really kind of sets the stage for what we're talking about here, size of atoms and interactions of atoms and molecules in component systems. Now, I always like to point out that in this treatise that Boyle put together, he made the rather prescient observation way back many years ago that perhaps the pressure of the air might have an interest in more phenomena than men have hitherto thought. And he put this in a chapter with the delightful title, Touching the Spring of the Air, in this wonderful treatise. So why should this be interesting from the standpoint of more modern thinking? Well, if we think about compressing atoms like this here, we start with a simple array of closed shell atoms, and when one compresses materials like this, or a system like this, one reaches a critical state where the electrons are no longer stable surrounding the atoms, and it goes into an itinerant or plasma state, and this arises because of the increase in the kinetic energy of the electrons. And a similar thing happens in a very simple sense with chemistry. When you compress a material, you reach a point in this simple picture where the electrons are no longer stable in bonds. They must distribute themselves in some fashion, and you go into some kind of dense plasma state. And this actually goes back to a notion due to a chemist, John Bernal, who pointed out that the ultimate state of molecules will be a metal or some kind of valence lattice. And this he put in a footnote, or was put in the footnote, of a famous paper by Wigner and Huntington that I'll point out. So if we think about the effect of pressure on materials, we think about our periodic table, and pressure tends to scramble the elements So we have simple structures for those elements that crystallize under ambient conditions. And under pressure, this orbital hybridization, which is the mixing of orbitals here, gives rise to complex structures. This is for the valence orbitals that can mix. But if we go to higher and higher pressures, and I hope to show some examples of this, we can go to really extensive mixing of orbitals, valence core hybridizations, and we're now seeing the signs of this in basically introducing an entirely new kind of chemistry in these materials. So let's think about compressing atoms and molecules in a different sense, some of the intuition and expectations. With increasing pressure, you have close packing, just a simple packing. This was the idea that pervaded us for many years. There can be increases in coordination. There can be orbital mixing, rather like what I described. And then ultimately, this idea that one has metallic character. However, this really is a very, very simple picture, and we need an entirely new way of thinking about this because we have mixing of all these different kinds of bonding patterns, and altogether new ones will emerge. So let's look at this in a little more detail in a thermodynamic sense. I like to use the example of cesium iodide, and here we're taking cesium iodide, this beautiful salt here, over the range of conditions found inside the planet, up to 300 GPa. So that's sort of the range of pressures found in the core of the Earth. And if we compress it, we have this equation of state for a solid, far different than what we had for the gases and the van der Waals equation of state. And if you compress that material over this range, you take it from an insulator to a metal, so the bonding changes. It's actually even a superconductor under these conditions here. And if you integrate this, you see the free energy change associated with that compression, and it greatly exceeds that associated with heating the material up to melting. So pressure is a wonderful knob, a wonderful way of tuning the energy landscape and taking this simple material and turning it into something altogether different, perturbing the free energies in terms of exceeding the bond strengths of the component bonds in the system. So how do we generate these kinds of pressures in the laboratory? There are really two classes of techniques, and I'll focus on one primarily. There are the static compression techniques, and this is a now quite famous drawing and schematic of how a beveled diamond anvil cell works. This is now able to reach pressures in the hundreds of gigapascals in range, and perhaps as close to as a terapascal. Here we're talking about perturbing energies associated with valence electrons, so EV energies, and I'll show examples of different kinds of devices now, more modern devices where we have a range of volumes that are possible and a range of different kinds of probes that are possible for measuring these materials. Now, another class of devices are dynamic compression devices, and this is a burgeoning area, and it's wonderful to see this being embraced here at the APS with the new sector. Here, in principle, at least on some of these platforms, one can generate hundreds of megabar pressures. So we're talking about very, very high energies produced by gas guns, magnetic drives, and laser drives. This is a picture of a laser drive, and I'll show you some examples of this and how we can use both kinds of techniques to understand some of the phenomena that's emerging. So here is really sort of a summary of all the different kinds of techniques that can be, kinds of techniques that one can deal with using static methods, including methods now to go to much, much higher pressure, shown here, using new kinds of diamond, CVD diamond probes of various sources, and then larger volume apparatus as well. Now, of course, here at the advanced photon source, we have a number of beamlines or sectors that are capable of this, and it's wonderful to see this expanding to other parts of the facility because of the opportunities for studying materials. There's also the NSLS-2, where we have a program here for using infrared spectroscopy, a successor of the NSLS, and also to complete the set of facilities we use for these kinds of experiments, the spallation neutron source for neutron scattering, where there's a dedicated beamline, and I'll show an example of how this is giving us new insight in combination with some of the X-ray and infrared work. So there are important applications here, and I want to show two slides that summarize this. there's the opportunity for producing altogether new technological materials, which is one of the drivers, of course, for DOE's investment in these kinds of facilities and in this kind of research. And we're fortunate to have an Energy Frontier Research Center dedicated to this, looking at energy conversion, structural materials, and energy transport, where the goal is to accelerate the discovery and synthesis of new energy materials using extreme environments, and use this information to extend the performance and lifetime of existing materials as well as to discover new ones. There's also an important programmatic need from the standpoint of national security science, and this underscores the need for the center we have here. This is the Carnegie DOE Alliance Center, which is an NNSA DOE-funded center to support materials for stockpile stewardship, looking at materials over a much broader range of conditions, including problems associated with ICF, but also practical materials important to the NNSA labs, such as particular kinds of hydriding reactions, high explosives, and the properties of high Z metals over a range of conditions. So both of these DOE needs we embrace in the work that we're doing. So what I'd like to do in the next part of the talk is really run through a series of examples. Some of them are really historical from the standpoint of the field, starting with simple molecules, moving on to the most abundant element, what I've entitled metals that are not, touching on planets to life. There's a very large component of the research done here at the APS, and a large fraction of our research is focused on Earth and planetary science. I'll just touch on a few examples there. And then there is the prospect of making altogether new materials, not just discovering new materials in extreme environments, but perhaps recovering them and making them of use for various kinds of technological applications. So let's return to Boyle's problem and touching the spring of the air. This is an example I like to use because it shows some very fundamental principles in a real system. So if we take air, or 80% of air, nitrogen, and compress it, what do we see? We see freezing on a lattice, rather like what I showed earlier in a notional sense, and this happens between 5 and 70 GPa at room temperature. But if one takes us to higher pressure and heats it, one forms an altogether new material. This is a beautiful framework structure, so we're driving up the coordination. You can see all the nitrogens are still have 3 bonds associated with them. Instead of the triple bond, the nitrogen has 3 single bonds in this framework structure, which you might call diamond-like nitrogen. This is a very interesting structure, and it took synchrotron radiation actually to resolve it in this beautiful set of measurements. It's a high energy density material because we've stored now this energy that was in the triple bond in the framework here. So it stores a great amount of energy, and it could in principle be used as a fuel or propellant. Well, let's take the other main component of air and look at a different kind of phenomenon. Okay, so this is a photograph of oxygen looking through the diamond anvils, and you can see this beautiful scarlet color. Nitrogen, in contrast, in this framework is a beautiful transparent material, rather like diamond. It's a beautiful large band gap insulator. This, in contrast, has got this beautiful red color. This arises because something unusual happens. There's a clustering of the molecules. You form these O8 clusters, and this arises from magnetic collapse. We know this from various measurements, and I'll point out just a different kind of measurement here. These are measurements were done a number of years ago at HPCat using X-ray Raman, where we probe essentially the electronic structure or the changes in bonding by looking at the K-edge, and the shifts in the K-edge allow us to rationalize this shift as due to back bonding as one stabilizes this cluster. So you have a kind of closed shell system forming in the cluster, and this energetic gain is better than it forming a transition to a framework structure. And I'll show another example of that in the case of hydrogen. So we have increased overlap of the bonds, and there's pi bonding here, and there's closed shell interactions that stabilize the cluster. And if one takes us to much higher pressure, one in fact produces a superconducting phase that emerges out of this with a low TC. Some very, very interesting physics. So let's take another simple system, simple in quotes, and that is water, which of course is a system of great complexity if you look in more detail. In fact, this points out the use of another way of using light on these systems to see something new, and that is looking at the compression. And here the question is what happens at very high pressure to the hydrogen bonding. This is old work that showed that with increasing pressure, here's an equation of state, one can take water, form these dense structures here to form ultimately this very dense form, which is known as ice tin. It's a symmetric hydrogen bonded structure with basically an oxide-like structure where the hydrogens are midway between the oxygens. Now, this was a very interesting finding, and it emerged because we were able to do infrared spectroscopy. That's how we first saw this using synchrotron infrared spectroscopy at the NSLS. And this is the structure that came from that and was subsequently confirmed by X-ray diffraction, including X-ray diffraction work done here. Well, just in the last few years, we found that here something quite surprising happens. Those measurements weren't able to probe directly the light atom sublattice. We can now do that, at least for D2O at the SNS. And when we take this system to those kinds of pressures, we see a structure that looks like this, where what we find is that, in fact, in the refinement, the hydrogens, or the deuteriums in this particular case, actually move off, or some fraction of them move off this position here between the oxygens. And so you have interstitial population of proton density or deuteron density. This is a split atom picture, so it looks like there are more light atoms in the structure than there really are, but this is a split atom picture, so the 25% of the atoms have moved into interstitial positions. So an altogether new kind of bonding. This actually looks much more like a metal hydride than water, or even the kind of oxide structure that we saw and inferred earlier from just the infrared and the X-ray measurements. And this was made possible by the advances we have in neutron scattering now, including the ability to do neutron scattering at a megabar pressure on systems like this. So now let's look at another example, or set of examples, and that is the example of the so-called simple metals. What do we have here? Well, if you take the light alkalis like sodium or lithium, we have this beautiful crystal here. In fact, understanding this system in electronic sense was the beginning of the modern quantum theory for solids. It has a simple structure, and it gave rise to actually the whole theory of quantum systems and bonding, understanding metallic systems from the standpoint of quantum mechanics due to the work of Wigner and Seitz. So what happens under pressure is also quite remarkable. What one has is an increase in transitions, an increase in coordination, ultimately the formation of complex structures, something far from what you have under ambient conditions, and at pressures like a megabar to a megabar and a half, very, very complicated structures. In fact, 17 or 11 different phases or 12 different phases of sodium have now been observed at room temperature or in the vicinity of room temperature and below. It also melts below room temperature at high pressure. And even more remarkable is when one takes it up to 200 GPa, one actually forms an insulator from this. So it's the reverse of the dogma that goes back to the very beginning of quantum mechanics, that all materials become metallic. This beautiful metal actually becomes an insulator at very high pressure. And the diffraction measurements that were done along with this were carried out at Jesse Cars here a number of years ago. So this was a very important breakthrough in the field. So how do we understand this? Well, it's really bonding without nuclei, so it's an altogether new kind of bonding. How can we understand this? Well, it turns out that early calculations that were done prior to this measurement showed that there can be in some cases the formation of interstitial electron localization. That is, in some systems like lithium in this model structure, which was proposed in these calculations, you can push the electron density off the ion cores into the interstitial region. So you form bond pairs due to this combination of repulsive effects and Pauli exclusion. You can also look at this from a chemical standpoint as the formation of an electride, and this is an alternative model that's been put forward. An electride, if you don't know, is a chemical system where a molecule can actually trap an electron or a pair of electrons in a hole, and you can use that to rationalize after the fact the stabilization of electrons in holes in these structures that would otherwise want to be close packed. Well, this can be also viewed as a formation of even quasi-molecules, and this is a set of calculations that we just completed and submitted. Similar things happen in lithium, and you see these beautiful holes in the structure, and if you calculate where the electrons are, you see what looks like a molecular form without nuclei, and Roald Hoffmann has turned these quasi-molecules. The challenge is now to understand this more fundamentally and actually do measurements, direct measurements, to confirm this sort of quasi-molecule character. But it really comes down to bonding without nuclei, or forming these molecular structures embedded in these metals without nuclear constituents. Well, one can do a little bit more elaborate work, and this is some work we've done looking at that same structure that was studied here in sodium. If one does higher level calculations, you can understand this in terms of SPD hybridization. If you just take this piece of the electronic structure in the top of the valence band here, see the nice band gap, you can understand why these holes develop. It's because you have SPD hybridization here that pull electron density away from this region and produce these holes in the structure. And you can actually develop symmetry principles for how one can predict when one goes into a state like this very unusual insulating state of a simple metal at very high pressure. So here again, the challenge is to do direct measurements of the band structure, and using techniques, for example, like the X-ray Raman measurements or some of the inelastic scattering measurements. In principle, in the future, we should be able to constrain this theoretical model further in terms of pinning down actually the nature of the band structure, and to really more tightly constrain the nature of the hybridization. So I've talked about some very simple systems and changes in electronic structure, metal insulator, metal transitions, and the reverse. This leads to the question of superconductivity. Superconductivity and high pressure have been together for many, many years. And here's a periodic table of the superconducting elements. Some 23 elements have been taken from non-metallic or non-superconducting states to superconducting states, even oxygen, as I mentioned earlier, and this list continues to grow. Also, the highest TC until recently was a material formed under pressure or studied under pressure, the mercury, barium, calcium cuprate, with a record TC of 164 Kelvin at 30 GPa. But as many of you know, now the excitement is focused on a very different class of systems, and that is the hydrides or the superhydrides, and H3S, or some structure that's similar to this, with a structure that appears like this, although there is somewhat controversial, does have, regardless of the structure, a TC in the neighborhood of 200 Kelvin at 200 GPa. So this is a very exciting development that's re-energized the whole superconductivity field, and is, of course, now very important from the standpoint of energy research, because there could be new classes of materials. This could be just the tip of the iceberg of a whole new set of superconductors with still higher TCs, and looking at other superhydrides or other materials with analogous properties, and perhaps ultimately having them recoverable and useful under ambient conditions. So I've talked about physical properties so far. Are there interesting chemical properties? Well, one can see a range of interesting chemical properties emerge under these conditions. I like to show this particular example because it's a nice segue into hydrogen. This is xenon hydrogen 2,8. This beautiful compound here. It consists of these dimers of xenon suspended in a sort of lattice gas of freely rotating diatomic molecules. We know this from the X-ray diffraction measurements carried out here, and one can actually do, over a range of conditions, refinements of the electron density. If you pull out the electron density at the very highest levels, you can see the electron density squeezed out from the xenon dimers, sort of reaching out into the hydrogen to hold this structure together. So that's something we can infer from this. We also know that it's an insulator under these conditions. It's stable to 250 GPa. We know that from infrared spectroscopy. Well, in fact, there's a whole range of different materials like this, these so-called van der Waals compounds or packing compounds formed by combining elements or molecules that don't normally want to combine under ambient conditions, starting with methane, hydrogen. This is H2O2, which is a novel clathrate. This was first discovered a number of years ago, and the single crystal work done at HPCat was finally refined in the last few weeks, and the paper to JAX was just submitted yesterday. So this is ongoing work. This is water in the quartz structure, but with hydrogen in the interstitial sites. There's this beautiful dense ice here, H2OH2, with a very high hydrogen content. This is the xenon hydrogen compound. And this is hydrogen sulfide plus hydrogen. In fact, this is a precursor compound to the one that ultimately forms the H3S. So studying this was actually very important for understanding the pathway to form H3S or other high-temperature superconductors in the hydrogen sulfide system. So obviously, there's a lot of interest in getting back to this and taking these kinds of materials to high pressure and look for additional superconductivity. So this is a nice segue into hydrogen. Of course, hydrogen has been an important problem for many years. And this goes back to the seminal calculation of Wigner and Huntington that I alluded to at the outset, where they predicted in 1935 that above some high pressure of 25 gigapascals, which was actually a lower bound in their calculation, this would transform to some dense form with a metallic character, that is, a conventional alkali metal. So what do we see? Again, very important in all of this has been diffraction measurements. Diffraction has been a great challenge, both neutron diffraction and X-ray diffraction. But early on, we were able to show that under pressure, initially one goes into a hexagonal close-packed structure. This was work that was first done at the NSLS. Neutron diffraction was done about the same time in the Soviet Union. So far, measurements have been done up to 200 gigapascal using a combination of single crystal and powder diffraction. And there's a need to extend this to higher pressure, in particular because of new phases that have been seen. So what are some of these new phases? We have to resort to other kinds of techniques. And here again, we use synchrotron radiation, now in the infrared. And one of the key discoveries made a number of years ago was the observation of this very large increase in absorption in hydrogen at fairly low temperature when increasing pressure. This was quite surprising because hydrogen, being a homonuclear diatomic, has no dipole absorption, so this shows there's obviously some kind of symmetry break-in. We interpreted this as an ionic transition. Instead of going into a metallic phase, it goes into an ionic form, which was quite a surprise. It took a number of years to rationalize the structure in terms of theoretical calculation. Well, we can do a wide range of other kinds of vibrational spectroscopy measurements using infrared and Raman principally, and with increasing pressure, you see these shifts in the so-called vibron or the intramolecular stretching mode. You can see breaks, which are signatures of phase transitions. One can see this weakening of the bonds, weakening of the molecules, but showing the molecules are intact over this very wide range of conditions. In fact, you can see evidence for weakly interacting hydrogens, strongly interacting hydrogens, but essentially the molecular structure is intact. So how does this map onto a phase diagram? So we can take the spectroscopic data plus the diffraction data, combine this on a phase diagram. Here, temperature and pressure. Here's the bound in the Wigner and Huntington calculation. We have these phase lines now. We have melting, transitions in the fluid from shock wave measurements that I'll come back to later, and then these transitions in the solid from principally the vibrational spectroscopy. So what are these phases? Also, this is the range of interest to the planets, which we'll come back to. What are some of these structures? Here's this disordered one that we know from diffraction, an ordered one from diffraction and some vibrational spectroscopy. This ionic phase, this unusual symmetry breaking phase, and then this new one here, which was discovered just a few years ago using vibrational spectroscopy that we're calling graphenic. So really quite different materials, all in the same element, quite different phases with different properties. I want to focus on this one in particular because this came as quite a surprise to many of us. We need ultimately direct structure determination, but what we have right now are vibrational measurements plus theory. And what that is showing is calculations of a very unusual structure with these sheets here of honeycomb layers or distorted hexagonal sheets that are graphenic between what looks like layers of nearly freely rotating molecules. So clearly very far from close packed, a very anisotropic structure. And we can ask the question, why should this form? Why should this rather open, unusual structure form instead of something simpler? Well, again, it comes back to looking at closed shell effects, an idea that is a part of basic chemistry, but now persisting in a very different regime. We have these units here that comprise the structure, these units of 6 atoms, and it looks like an aromatic system. So rather like benzene, a conventional aromatic hydrocarbon, we have a graphenic unit that, when one calculates the stability, imparts the stability that overall gives enhanced stability for the entire structure. And you can see this when you do simple molecular calculations. Here's hydrogen as a hydrogen ring structure is just a piece of that as a function of ring size, and you can see that there are magic numbers that appear that have enhanced stability, just like you have in the case of benzene or conventional aromatic systems in hydrocarbons. So you have a Huckel's rule that you may recall from freshman chemistry that pertains in this system over this very wide range of pressures, very high pressures indeed. And you can see it's also quite independent of the level of theory one uses. This is actually a distorted structure, so you can actually see in the calculations when you distort, you have motion associated with the hydrogens moving in the plane of this structure, that this stabilization pertains. So both the distorted and the ideal form are aromatic, and we believe this is why this particular structure exists over this domain of pressures. Well, is it metallic? One of the central questions. We're far above the bound presented by Wigner and Huntington. We can use, again, synchrotron infrared spectroscopy, use a non-invasive technique to look at the optical conductivity. And if one does this, one can probe down to fairly low energies, long wavelengths, and you see very transparent material with perhaps some upturn here, which could be associated with very weak conductivity or a small Drude feature. These are model Drude calculations, assuming a simple degree of band overlap. What this means is that the plasma frequency of this material at these conditions is very low if it's a metal. It's quite dark in reflectivity. There is a possibility of a weak upturn, which would be consistent with some conductivity measurements that have been reported. So if it's metallic in this region, it's a very poor metal. It's dark like this, so what this means, in fact, is the system really is much more like graphite, than it is like a conventional alkali metal. So it's really a new picture for the metallization of hydrogen, and you can see that from this comparison of the calculations for these different structures and what we measure. It's on the borderline of a semiconductor semi-metal between these pressures of sort of 200 to maybe 400 GPa. But there is the possibility that perhaps it transforms to a semi-metal in this range as well. But anyway, it's a very different picture than what has emerged over the years. Of course, we'd like to go to higher pressures in the solid, look at the band gap as a function of pressure, and look at the high pressure behavior of the fluid. Well, we can probe the band gap, and in fact, one can do this in principle using X-ray Raman measurements, and some very preliminary work was done a number of years ago. There have been some improvements here, rather like the X-ray Raman measurements. So because we are above the band edge for the diamond, we need to probe this region that's a no man's land because of the absorption of the diamond, but we can scatter into excited electronic states, just as we can scatter into vibrational states in conventional Raman, and you can see a structure that looks something like this. This is interpreted in terms of the band gap and the excitons, and this is early work that was done on the order of 11 GPa. There's a lot of background to worry about from the gasket here. Of course, we're doing the measurements coming in from the side here. But one thing that's quite interesting is that this structure is very similar to what's seen for the one photon absorption under ambient conditions, indicating that the band gap is largely unshifted over this range of conditions. But we need to take it to higher pressure to watch for actual closing of the gap. Another interesting finding, and this is work that we've just done in the last year or so, is there may be altogether new kinds of physics associated with this, the possibility that some of these phases that are being observed could be topological semi-metals, and there could be surface metallization in addition to bulk metallization that we would need to understand. And one of the predicted structures is this one right here. And if one looks at that carefully, it's a topological semi-metal, which means it could have very high surface conductivity, which could be something that we would have a signature of in infrared absorption or in conductivity measurements. And you can see that from the large peak in the density of states here at the Fermi level. So this idea of interfacial metallization is something we need now to understand and constrain as looking for transitions like this in hydrogen and in other systems. So now I'd like to step back and look at this from a planetary standpoint. And what motivates this, of course, is the rich variety of bodies that have now been observed throughout the cosmos in terms of planetary science. So this is a plot of the relative size in Earth radius versus temperature of the thousands of exoplanets as of 2013 that really provide an important way of making contact between our measurements on materials under extreme environments with what planetary astronomers are providing. So let's just take, however, our closest large planet, Jupiter, and ask the question, what can we say about the experiments we're doing now in terms of the composition and some of the properties of Jupiter. This is a very simple model. This comes at a very interesting time now because next month, the Juno mission will end with the probe entering the planet to give us information about the origin and evolution of Jupiter, the composition, including H2O, the gravity and magnetic field internal structure and size of a core. So these experiments we're doing here on Earth, in principle, can constrain some of this or be an important way to ground truth some of the observations that will come from this very important mission. So now let's go back to the phase diagram, plotted a bit differently. Here's the range I showed earlier at low temperature. We're interested in this region up in here, and the question is, does one have a transition from an insulating fluid to a conducting fluid? This is the geotherm or the PT path that one would follow if one entered that planet. And here we're using the largest laser on Earth, the National Ignition Facility, to explore this range of conditions here. This was actually created to go to ICF, much, much more extreme environments, but we can use this marvelous tool to examine this much more modest range of conditions that we can't access really any other way. So what we see is shown here. Here we see we're measuring reflectivity. This is a sample geometry. The laser pulse comes in. We have a thin film of deuterium, and we measure reflectivity, rather like what we do with a synchrotron in a diamond anvil cell under static conditions. And we see this rise in reflectivity here that shows that there's some kind of transition, ultimately, we believe, by 200 GPa to a conducting fluid. So this is a preliminary plot of what we've observed so far. We see that I showed a range of different shockwave profiles for this transition. It collapses down into this region here. So we think this is the transition region from this insulating fluid to this conducting fluid. We obviously need to go to much higher temperature and to lower temperature to constrain this better. What this means is we have reflectivity that shows in our model 100% dissociation by the time you get up to about 200 GPa. And this is at a lower pressure than some previous measurements that were reported just recently in Science indicated. So as I pointed out, we need to extend to higher pressure, higher temperature and lower temperature. And if we can get to lower temperature now, using this tool in a very different way, very careful ramp compression, isentropic compression to probe the low temperature state, we could in principle look at some of these really exotic phenomena that are predicted here and ask the question whether it's actually a solid under these conditions or perhaps this novel state of matter, this predicted superfluid superconductor. Another thing we can do is ask questions about the size and existence of the core of Jupiter or similar bodies. And here we need to recognize that there is a great wealth of new chemistry that one needs to now take into account. And one can see this when one does now just static compression experiments on so-called unreactive or inert metals. What we're finding at conditions associated with the very high pressures and high temperatures of bodies like this, all these materials soak up hydrogen, so you form a wide range of different kinds of hydrides. This comes from both theoretical calculations and some experimental reactions. So we're making the prediction that the extreme reactivity of hydrogen with metals like tungsten or core materials found in these large planets will erode any core that might have existed. So we're making the prediction that there could be a density gradient, but no distinct core associated with this because of the intense reactivity of hydrogen with these kinds of metals under these kinds of pressures, which are on the order of tens to 100 megabar pressures. Well, another important component of this is ice, is water, another thing that will be looked at in the case of the Juno mission. And here again, we have more complexity in the case of hydrogen. Here's the symmetric hydrogen bonded structure, our refinement with this interstitial proton density, but the wealth of different phases now that are seen here, and these are the different PT paths that one infers for different planets. So the question is whether phases of ice, phases of H2O in this range here could contribute compositionally and in terms of the dynamics, including the geodynamo of some of these bodies as more and more are discovered. So another component is carbon. What happens to carbon in combination with hydrogen? This is actually an interesting question from a planetary perspective. It's important also from the standpoint of our high pressure experiments, because in many of those experiments on hydrogen, we have hydrogen in contact with diamond. So what can we expect for hydrocarbons at these kinds of conditions? These are now just theoretical calculations that are driving some new experiments. So here we have the hydrogen-carbon binary. What we're doing is a series of genetic algorithm searches for different structures. And in fact, we find a wealth of different structures that are marginally stable relative to diamond and metallic hydrogen under these conditions. And some of these are shown here. They're really quite unusual structures. So these are structures that could be seen in the laboratory now. They could be also important structures of materials inside some of these hydrogen-rich and carbon-rich planets at extreme environments. So again, this has important implications for planetary interiors, and it's also very important for understanding better the interactions between hydrogen and diamond in our diamond anvil cell experiments and various ways we may need to contain hydrogen better to look at some of the exotic physics that's being predicted for these systems. So can these experiments be done at much, much higher pressure? Again, using the National Ignition Facility, some beautiful proof of concept work has been done now on pure carbon, on diamond. These are breathtaking measurements of compression of diamond to 50 megabars. So rather like the experiments I just described for hydrogen, but now for diamond, this is ramp compression or near adiabatic compression, that is compression with minimal heating. One sees this beautiful equation of state here, comparison to lower pressure data. And really this is now opening up a whole new vista, a whole new a set of problems that can be looked at, or these kinds of pressures, using this tool that was developed for ICF now as a tool for material science, and in particular one that can be used for making contact with observations from planetary astronomy. So let's return to Earth, and just very, very briefly, of course, this is a very, very large subject, the study of the materials of the Earth, and I just want to point out a couple of examples. First of all, this has been an explosive field looking at the structure of the mantle and core, and as many of you know, in the last few years, part of this has been motivated by the discovery of altogether new forms, the post-perovskite forms and related structures that exist at the base of the lower mantle. But in addition, there have been interesting observations and experiments that show that the behavior of volatiles can be quite different under these kinds of conditions. In fact, altogether, new minerals in principle can be made from volatiles like CO2. This is the structure of a mineral or a possible mineral of CO2, pure CO2. It's polymerized into a structure that's cristobalite-like. So it's a framework structure somewhat similar in a sense to what we have in the case of nitrogen, taking this closed shell system but polymerizing it, driving up the coordination of carbon from twofold to fourfold, and we find it's stable of the entire pressure range of the lower mantle. So it could be an interesting natural mineral for sequestering CO2 inside the planet. It's not stable in the upper mantle, or at lower pressure, but it could be a reservoir of a vast amount of CO2 in the planet, of carbon in the planet. And this is all done under the auspices of another program called the Deep Carbon Observatory. Well, this takes me to another set of questions, and then the question of life in extreme environments, and using these techniques, or some of these techniques now, under a much, much more modest range of conditions and looking at very delicate structures, soft matter, and even biological systems. So what can we say about the behavior of organisms or the components, the soft components of these organisms under pressure? And this actually is important for understanding the limits of life and the range of the habitable zone of life as we know it on Earth as well as elsewhere in the cosmos. Well, this is an area that only is just begun in a sense with a few studies over the past few years. One can do elegant structure function studies of enzymes, for example, these pioneering studies of lysozyme that were done at 7 kilobars by Roger Ferme. Also at HPCat early on, studies of viruses showing that there can be interesting changes of viruses now under just a few kilobars pressure, but clearly very large molecule crystallography can be done to look at structure function. One can also look at whole organisms using these techniques like diamond cell techniques developed for physics, chemistry, material science, applying them to biology and looking at whole organisms. And in early work that was really quite controversial, where we claimed microbial viability of some microbes in the 20 kilobar range, this has been confirmed in some recent work, which in fact showed that there can be directed evolution. So putting microbes under pressure and then successively pressurizing the surviving communities can be used as a way to direct evolution, which has some pretty profound implications for evolution as a whole, and interesting questions about how adaptation is occurring and how this is affecting the genome. This has important implications for life elsewhere, including possibly life in the deep watery regions of some of our familiar moons in this solar system, like Europa. But it also cries out for sort of a new way of looking at this in terms of whole organisms, using new imaging techniques like those developed at the ALS for looking at organisms under near ambient conditions, but doing this under stress in high pressure apparatus to understand just what's happening in these structures and in combination in entire organisms using both time-resolved methods and the new X-ray imaging techniques that hopefully will be coming online here. So I just want to close with just a few examples of the new technological materials that are emerging from this. Really another new avenue for some of this work in the last few years. And as I pointed out, this is the focus of our Energy Frontier Research Center. Just highlight 5 here very quickly. The discovery of sp3 nanothreads, a discovery of porous structures, something that was really quite surprising. One can use pressure to make a porous material, a truly porous material, which seems like an oxymoron, but one can make porous materials under pressure by combining components, removing secondary chemical components, and what you're left with is altogether new structures that have the framework of a high pressure phase, but in fact can be low density. This is very important for catalysis, for thermal management, and there could be some other interesting applications energetically. Related to that is looking at new solar materials. This was a marvelous discovery. The diffraction work was also done here at APS. The discovery of silicon-24, which again was formed by making it pressurizing the clathrate, removing the secondary components, and what one is left with is a new form of silicon, a new polymorph with a direct band gap. So a pretty revolutionary discovery. One can also use pressure to understand the dynamics of systems, that is, how lithium moves in batteries, so looking at the energetics of diffusion by just pressure tuning of the system and understanding the energy landscape. And also, finally, coming back to superconductivity, using these discoveries of these new classes of superconductors at very high pressure, exploring a wider range of composition, and actually tuning the composition to form materials that could be stable or recoverable under ambient conditions. And this is a prediction that we have for something that's quite similar in a sense electronically to what one has in the H3S compound, but in the carbide system with a relatively high TC. So obviously we're very interested in trying to make these and related materials. I wanted to show just one example in a little more detail, and that is the example of the nanothreads, because this was a very important breakthrough, and some of the work is being done now, even as we speak, here at the APS to understand aspects of this. This was a very interesting discovery. It was discovered by accident, in effect, because it comes from pressurizing benzene, and what one finds is that one can fill out this matrix of carbon nanomaterials. So here we have sp2 bonding, sp3 bonding, the zero-dimensional, one-dimensional, and two-dimensional cases for C60 nanotubes and graphene. Here we have graphane for sp3 and then diamondoids, little pieces of diamond that are decorated by hydrogen. And what the nanothreads have done is fill in this matrix with this one-dimensional structure, all based on sp3 carbon. Now, this is really quite interesting in a number of ways. Again, it was discovered in effect by accident, by compressing benzene and decompressing it at the appropriate rate. So time dependence is very important. It appears to happen via some kind of cycloaddition reaction like this, but just how this occurs, how this very anisotropic structure occurs on hydrostatic or near hydrostatic compression is not known. So we're doing in situ measurements of the mechanism right now. It's predicted to have very high strength, So it could be a marvelous new material, and it could be functionalized in various ways to make it a useful energy material or technological material for other kinds of applications. Well, finally, what we'd like to do ultimately is scale all this up. One can do this with larger and larger high-pressure apparatus. One can also use what I've just described as a sense of discovery science for the existence of new materials, new compounds, and then devise new ways of making them, alternative routes for making them. And the best example of that, and the one we like to highlight, is the example of diamond itself, which of course was first made made in a reproducible way by General Electric in the 1950s, forming these nice little crystals of diamond with very large presses. But now we would like to extend this further, increase the size and quality of those kinds of materials and the materials recovered from nature, and then optimize them in different ways. And a number of years ago, we adopted a program to do this using chemical vapor deposition, using single crystal techniques, starting with a single crystal, and found ways in which you can actually augment a single crystal, do single crystal growth of diamond, which of course is a high pressure phase. And here you're using kinetics to bypass thermodynamics, biasing the reaction toward the formation of the sp3 carbon instead of the sp2. So we have some idea about the mechanism of this, but again, a detailed understanding of just how it's happening at the surface isn't clear. So this is an opportunity for studying in situ, for example, using synchrotron radiation or various surface probes for really understanding this better, and then using what we learned there to apply this to other materials so we can take some of these high pressure or dense materials formed in other ways and use these more accessible methods, or methods that will allow us larger and larger quantities to be developed. So this just shows an example of some of the crystals we've been able to do. But to date, we've produced a number of different crystals for anvils. We can also use them for other kinds of applications. For example, coming back to the application of X-rays, we can produce these nice windows that have already been used for small angle scattering experiments at Cornell, for example. So to conclude, I think the future is bright for this field, and in particular, bright for the APS with the upgrade of the high pressure sector, the DCS sector coming online, implications for the other sectors. Also, we're excited by the developments of the NSLS-2 to continue the infrared work. And then we have these other facilities that are proving quite important, that are also shedding new light on materials using very different techniques. So taken together, they represent a nice collection of facilities that are very important to this field, and it involves a very important partnership between Office of Science facilities and NNSA-funded facilities. So that's really crucial for this field going forward. So scientifically, high pressure is opening up a new world of materials. As I pointed out, the implications span the sciences, and there's really a close synergy between theory and experiment here. It's very important for continued growth in the field. The findings provide new insights into the behavior of materials under normal conditions. So we're learning a lot about the behavior of materials in exotic environments, but that information is really telling us quite a bit about more familiar chemistry, and that's quite important. Light sources have enabled these developments in major ways. This could not have happened with the range of lights, without the range of light sources we have available to us. So indeed, the future is bright for the creation of new facilities and developments with those new facilities and developments underway. So I would be remiss if I didn't thank a large number of collaborators. These are the principal collaborators at the Carnegie Institution, including some of the lead collaborators at HPCAT, but actually it's the entire team at HPCAT that's been very important to us. These are the lead scientists at some of the other institutions, and these are the agencies and institutions that principally supported this work: the Energy Frontier Research Center, the Carnegie DOE Alliance Center, that's funded by Office of Science and NSA, respectively. The Deep Carbon Observatory is a 10-year effort to understand all aspects of carbon in the planet. It's now in its 6th year. NSF contributed to a number of projects, and in particular, it's been the COMPRESS consortium that supported very nicely the NSLS facility over the years and made those experiments possible. And with that, I'll close with some more pictures of our diamonds. Thank you.
I'm sure our speaker would be happy to entertain some questions.
So thanks a lot for it's a wonderful talk. I enjoyed it a lot. I'll make a footnote. I had the pleasure to actually work with Hillard Huntington when I was an undergraduate at RPI. So it's kind of fun to see stuff he did 80 years ago finally, crystallized, so to speak. But I was curious, you talked about the hydrogen stuff twice, and when initially it looked like it was forming these very exotic faces. But when you talked about it in terms of planetary work, you referred to this metallic hydrogen as well. So, is there still like a liquid metallic hydrogen that's existing, or is it just these very exotic, complicated solid structures that you were seeing?
Yeah, that's a good point. There are really two separate problems here, in a sense. The transition in the fluid is the one that's relevant to the planets that we know, the hydrogen-rich planets that we know. There's no evidence for those solid phases, which all have fairly low melting temperatures. And so the question there is, what's the nature of that transition? Ultimately, it should become some kind of dense conducting plasma, which must exist because these bodies, like Jupiter, have very large and chaotic magnetic fields. Just where it is and what the nature of that transition is one set of questions. What happens in the solid may be related in some sense, but really you're talking about a system where there's this crystallographic control. You have these exotic structures, something that may be more like graphite or a topological semi-metal or a topological superconductor. That may be related to what's happening in the fluid, but in a sense it's an altogether different kind of problem and involves a very different set of techniques, largely. That was just for the solid phase, that's right. But it's been kind of used loosely as a model for the fluid, which is not quite correct.
I have a question, Russ. I remember you guys coming when you were young, and when I was young, to workshops here to make the scientific case for APS. And one of the things you guys were very hot about at that time was that you're going to solve the problem of composition of the Earth's core. All right, and 20 years passed, and I still see papers which says, I swear it's iron carbon, I swear it's not iron carbon, something else. So you didn't touch upon in your talk today about the Earth's core. Where do you think that problem is going, and how much progress was made, actually?
Well, that's a very fair point. That problem goes back to the early 50s when Francis Birch actually made the conjecture that a large number of additional elements should form along with iron. And the extent to which we've improved on the 1950s is incremental. Having said that, we do have some bounds on what that composition is, whether the light elements are hydrogen, oxygen, sulfur, and silicon, or some combination. But it's a very difficult one to get a final answer to. So progress, I believe, is relatively incremental on that whole compositional question. That's just my personal view.
Russ, that sixth form of carbon that filled in that question mark in your table, was that produced at high pressure, and is it stable? Is there a material that was isolated that's stable at
it's recoverable.
Normal pressure?
So the materials in that last part are all recoverable materials. That's right.
Anyone else? If not, let's thank our speaker again.